We all know that feeling when you visit the bathroom and get that uncontrollable rush of adrenaline when you see it, hanging on the wall like something from the finest of art galleries. While you do your business, your mind starts to wander. How fast does that motor spin? How's it controlled? How does it detect my hands? Then you snap back into reality and go to claim your hard-earned reward. I recorded an intro, but it was really boring, so let's get straight into it, starting by looking at a few noteworthy things on the outside before we take it apart. This connector on the back is where the mains power comes in. Despite this being a British product, they're using the American wiring colours, which is a bit disappointing. Here's the label on the back, not much of note really, other than the 900 watt power rating, and lack of universal input voltage. Presumably there's a different version of this hand dryer for lower voltage countries. Yep, we can see in the spec sheet there's a low voltage variant of this hand dryer for low voltage people. And it appears it was made in Malaysia. Shout out to all the Malaysian viewers. This is quite interesting. On the bottom, there's a switch between 900 watt and 650 watt, which I think Dyson refer to as eco mode, so it'll be interesting to see what's going on internally to differentiate these power levels. The fixing mechanism onto the wall plate is very simple, it just hangs from the top, and then there's a pair of small screws in the bottom to stop it coming off. And the last thing we'll look at before we start stripping it down is the path for the airflow. You can see these two vents at the top of the rear where air is drawn in before it's passed through this HEPA filter, which seems a little bit unnecessary for a hand dryer in a bathroom. After that it passes through the fan compressor thing before entering the branches and hitting your hands. So the first step of the disassembly, and probably the only part we can do without any tools, is removal of this HEPA filter. As you'd expect, there's not a lot going on here. You can see the two side intakes and then the central exhaust with a nice seal to make sure none of that dirty, unfiltered toilet air makes it through onto your hands. I think if we pull it, there we go, we can get the actual filter out, which looks pretty clean really. Though I suppose if this has been used in a public toilet, this stuff might not be very nice. At the bottom of the hole for the filter we can see the intake for the compressor, and if I line everything up nicely we can see the motor in there. So that's nice. Yay! Very nice. I really hope that's mud. Right, before we move on to the main compressor section, let's take a quick look at what's going on this small auxiliary circuit, which is clearly in charge of turning the hand dryer on and off, as well as controlling its power level. Now before we look at this PCB any further, I think it would probably be worth removing the internals of the branches, just to give us a better idea of what these two connectors connect to. I must say I'm a big fan of this yellow, it's giving proper retro Dyson vibes. It's a shame that in the finished product, the only part of the yellow we get to see is this little smiley face. And there in the corner you can see the little hand sensor. I'd love to know how much engineering and simulation and testing went on to decide the perfect width of this little slit that the air gets forced through. How sweet is this? This PCB's got a tiny little copper Dyson logo in the corner, and it looks like they couldn't quite fit it in horizontal, so it's got a bit of an angle on it. I do like that. Now there's a bit of a plastic shroud surrounding what I presume are transmitter and receiver. Let's see if we can pop that off. Ah, it's squishy. And it's all one package as well. Hopefully there's a part number we can read. Nope, there's not. But knowing that this kind of thing is typically done with time-of-flight sensors these days, I thought I'd try my luck on Google, and what would you know? There it is. The good old VL53L3CX from ST. This uses frickin' laser beams to detect nearby objects based on how long it takes to see a reflection, a bit like sonar. It's got some quite advanced features like multi-object detection and smudge compensation. But most exciting for us is that it uses a simple I2C interface, so a few lines of code is all we need to have a play. Before that, however, we need to do a little bit of reverse engineering. Here's the pinout given in the datasheet. For some perverted reason it's a bottom view, so we need to flip it upside down to see how it relates to the various traces on the PCB, which all end up at the 6-pin connector that links this sensor board to the one with the power level switch, which basically just contains a microcontroller, a switch, and a lot of boring passives. As we now know the pinout of this 6-pin connector, I've made this little breakout board, which allows us to easily interface with an Arduino. This Arduino circuit then connects the hand dryer to the laptop, which is running some code that I definitely made myself, which shows us the output of the hand sensor telling us how far away our hand is from the hand dryer, or at least from the sensor. As we saw in the datasheet, there is a lot of stuff that you can configure this sensor to do, like detect multiple objects, and it also has multiple zones, so in theory it can detect what direction your hand is moving, whether you're moving it up or down or left or right. But this is just a quick demo to show that this sensor is something we can talk to ourselves. Quite nice. Right, time for the compressor. Are you excited or what? Nice. Not much to see from this end at the moment, except some interesting looking mesh, presumably doing clever fluid dynamic things. Wow. Whatever these mesh things are doing, it's quite interesting. 1,
2, 3, 4.
5, and a little filter thing. Really weird. I'm guessing they're to sort of break up the vortices a bit like those things in wind tunnels, I think. But I'm sure there'll be many of you watching who can give a much better explanation of what these are doing. So here's a better view of this kind of mesh thing. Hopefully this is enough for a fluid expert to tell what's going on. Very funky. Right, now back to the main housing. This front panel should unclip. Oh. This looks like an input filter. Yep, not a lot going on there, just a big common mode choke. For some reason the main input connector has sort of what I can only describe as suspension. Not quite sure why. Between the input connector and the common mode choke, there's this heat shrink on the white wire, which looks like it's probably got a fuse in, but let's cut it open to see just in case. Yep, no surprises there. Looks to be an 8 amp fast blow fuse. So, yeah. Why don't we cut it off and see if it's got any sand in it? Yay! Nice and sandy. So it's looking like all the control electronics is contained within this housing as well. Hopefully yanking on this doesn't damage that at all. But it does make sense. I imagine it'll be using the massive amount of airflow as forced cooling. Hopefully you can make out in there a pair of spade terminals. I'm going to try and pry them off. There's one. There's 2. Yay! Here's the main compressor, fan, turbine unit, whatever you want to call it. It's got some nice weight to it. Right, let's take off this cable tie, see if that shows us any more. Now, a small concern is that I don't see any more screws. I just see glue. You can see the rotor in there. It's got quite a lot of cogging torque. That's nice. Dyson. Lovely. Let's connect it back up and see what happens if we try and turn it on. Right, I'm slightly concerned about the startup torque and the rotor inertia being so much that the motor just f***s off. There we go. Perfect. This setup looks really safe. We've basically got the original hand dryer rebuilt. I've even used yellow tape for the sensors so they can feel at home. All that's left to do is plug into the mains. And without further ado, let's power it up. 3, 2, 1. That was quite loud. I'm wondering if there's any nice way we can try to measure the RPM. I've got a little tachometer thing. Right, ready to go. You can see on the end of the rotor here, I've put this square of shiny stuff. That's for the tachometer to look at. So every time it sees that reflective material passing by, it knows the rotor's turned 1 revolution. And in theory, we can just count those up and find out how fast the rotor's going. This is so scary, oh my god. 3, 2, 1. Right, well that was about 70,000 RPM, which is quite quick. Here's the main compressor next to one from a handheld vacuum from Dyson, maybe about 10 years old. And despite the age and price difference, we can immediately see quite a lot of similarities. Of course, the single biggest difference is that while the compressor from the hand dryer is designed to blow, the one from the vacuum cleaner is designed to suck. And one key difference that results in is the single central inlet hole on the vacuum cleaner compressor, in contrast to the large, thin exhaust that runs around the perimeter of the hand dryer compressor. And that's just because as the impeller spins, it throws the air outwards, so the outlet will typically be circumferential, while the inlet will be central. Before we open up the hand dryer compressor, let's take a quick look inside this one, as a bit of a benchmark to compare against. And the first thing we can see is that this compressor does in fact have exactly the same circumferential exhaust. It's just that, of course, in the case of a vacuum cleaner, the inlet is the end of interest. Now, I must admit I've bought quite a few of these old handheld vacuums to get the motors out because I'm quite a fan of their design. They're really well cost optimized. A great example of this cost optimization is the rotor, which is just a single diametrically magnetized cylindrical magnet. You can see it following the screwdriver here. The whole stator and controller assembly is also delightfully simple. The stator might look a bit funny because it's a single-phase brushless DC motor, so both magnetically and electrically there's not a lot going on. If I bend these two caps out the way, we can get a better view at the driver board, which is basically just 4 MOSFETs forming a H-bridge, allowing current to be passed through these coils in either direction. Position feedback of the rotor is done using this small Hall effect sensor, which sits in this gap between the two sides of the stator. And on the back side of the PCB there's just a microcontroller, a gate driver for each MOSFET, and some other less interesting stuff. What is interesting though is JLCPCB, who offer shockingly affordable high-quality PCBs. Their 6-layer boards are now available with a free upgrade to VIA in-pad technology and gold plating. The additional layers versus 2 and 4-layer boards allow for faster, cleaner routing, so you can spend less time on boring development and more time on fun testing. New JLCPCB customers can receive a $30 coupon for use on 6-layer boards, and a 48-hour production time means you only have to wait a few days to receive your 6-layer goodies. So, what are you waiting for? Check out JLCPCB after you've watched the rest of this video, using the link in the video description. Right, now I've been putting it off for a while because it's pretty much inevitable that as soon as I open this, I'll think of another test we could have done. But I've got bored of trying to plan ahead, so let's take it apart. That was nice and easy. Hopefully the rest of it comes apart that well. Of course, we can now see quite a lot of circuitry on top, but we'll take a closer look at that later on. One thing that I find quite intriguing is these enamelled wires that come down around the outside of the Y-cap. They appear to be a different gauge to the wire used for the stator windings, so I'm not quite sure what they're doing. Yay! Right, here we go, we've got the two parts separated. I'll just tidy them up a bit and then we'll take a closer look. But just before that, these two mystery wires seem to go down to some kind of magnetic component deep in here. You can just about see part of it down in that hole. Looks very interesting. Not quite sure what it is. So here's the power electronics. It's quite similar to what was in the vacuum cleaner. 4 switching devices, this time IGBTs rather than MOSFETs, which is quite exciting. This runs at much higher voltage. One thing I quite like is how little surface area these heatsinks have. Because there's so much airflow, there just isn't really any need for surface area. And again, similar to the vacuum cleaner motor, we can see a Hall effect sensor here for rotor position feedback. There's a fat rectifier here to take the mains AC into DC, but interestingly very little capacitance. It seems to just be using these 2 film capacitors. And I think I've just worked out what these mystery connections and that strange toroidal thing in the motor do. I think that's just an inductor for power factor correction, and they've just buried it inside the motor because that's a nice place to put it. And when we take a look at this simplified schematic, we can see that is indeed the case, with the toroidal inductor in the motor making up a big part of the input filtering, along with the common mode choke we saw earlier and these 2 film capacitors. After the mains input has passed through these filter components, it reaches that big rectifier package containing 4 diodes that turn the AC into DC. That DC then needs to be smoothed out, which is the job of these blue film capacitors, though a total capacitance of just 4.4 microfarads suggests it probably isn't that smooth. For comparison, this tiny little Anchor power supply has a 33 microfarad capacitor, and it's only 30 watts, while the hand dryer is 900 watts. It's an interesting design philosophy. Use the smallest possible DC link capacitance to save on cost and size, and then just use a huge filter inductor to keep all that horrible high-frequency ripple and noise inside the drive, blocking it from reaching the mains. As we saw, there's 4 IGBTs forming a full bridge, allowing the DC link voltage to be connected to the motor windings in either direction using pulse width modulation or PWM, allowing for control of the current, which is measured by sensing the voltage drop across these 30 milliohm shunt resistors. Let's now quickly take a look at one half of the full bridge, where we can see the gate driver circuit that turns the IGBTs on and off, as well as a MOV or metal oxide varistor to clamp voltage spikes, protecting the IGBTs. There's also a small multi-layer ceramic capacitor that provides a little bit of higher quality capacitance, closer to the IGBTs than the film ones. This capacitor is here to deal with the overshoots and high frequency ringing that occurred during switching that the film capacitors with inferior parasitic resistance and inductance aren't as good at handling. Looking closer at the gate driver circuit, there's not really anything special going on here. They're using a fairly typical half-bridge driver IC and asymmetric gate drive, where turn-on current passes through the top resistor, while turn-off current also passes through the lower resistor because the diode conducts, allowing the gate of the IGBT to be discharged much faster than it's charged, which is handy for reducing overshoots and EMI at turn-on, while minimizing switching losses at turn-off. When it comes to non-power things on this board, there's a PIC microcontroller for controlling things, and a buck converter for powering all the low voltage bits like the hand sensors and the aforementioned microcontroller. There's also this NTC thermistor for measuring the ambient temperature of the airflow around all this electronics, so the hand dryer knows if things are getting a bit toasty and can turn off. Now before we take a closer look at the motor, I want to try and get this end off, though it does look very well glued on. Right, that's now allowed us to see quite a lot, which is exciting. We can see the impeller on top, and we can also now get a closer look at the exhaust and its structure. So there's this main transparent section, and you can also lift it off to reveal a separate white piece, both of them containing numerous turning veiny things. Unfortunately, despite my best efforts to pretend I know what I'm talking about, I can't really go into detail on what these are doing beyond just directing the airflow. But once again, I'm sure some of you can. And now for the most exciting part, the impeller and motor itself. Trying to turn this, the cogging torque is once again very visible. And this is the cause of that strange boinging sound that you can hear in the majority of Dyson products, hand dryers, hair dryers and vacuum cleaners, anything with one of their very high-speed motors. This so-called cogging torque is a result of the attraction between the very strong magnets on the rotor and the steel of the stator. It's particularly pronounced in these motors because they have an equal number of magnet poles and stator teeth, meaning when the rotor is in its happy place, all of the magnetic fields are perfectly aligned. This is in contrast to conventional three-phase motors, where there are always more teeth than poles, meaning whatever position the rotor's in is never fully magnetically satisfied. Applications that have something important attached to the shaft of the rotor, like the wheel of a car, require minimal cogging torque. Otherwise your car will feel like this when you're going slowly. It's a bit outside the scope of this video, but if it's something you'd like to see covered more, let me know. Now there is something very exciting about this rotor, which we're going to take a look at in a minute if we can get it out, but if any of you think you know what it might be now, leave your guess in the comments. On the top of this assembly next to the impeller is this O-ring which I accidentally noticed earlier comes out, and when we take it out, everything becomes nice and loose, and I think it might even let us remove the rotor. But before we can remove the rotor, there's something we need to do to make sure we don't damage it. At the moment, there's a very small gap between the rotor and the stator to allow it to spin, called the air gap. Once we remove that O-ring, the rotor will become loose, and its magnets will pull it into the side of the stator. That means when we come to pull the rotor out, the sharp steel of the stator is going to scratch it. So, to protect the rotor as we remove it, what we can do is insert some paper into the air gap between the rotor and the stator. We can't use any old paper though, because the combination of the strong magnets and the sharp steel will basically just act like scissors and rip it apart. So what I'm going to use today is a small piece of Nomex, which is basically super paper. Sometimes it can be quite fiddly to get this on. Right, I think that's about as on as it's going to get. Let's pry off that O-ring and see what it does. You can see this internal piece of plastic is now loose, and if we flip everything around, you can just about see that the rotor's also loose. Oh my gosh, that is extremely exciting. Not only is the rotor out, but I've got myself a new ring. And you can see now how the Nomex prevented the rotor from rubbing on any of the stator, as it pokes out on the other side too. Like in all motors, the stator is made up of many thin layers of steel, electrically insulated from one another to prevent circulating eddy currents from flowing. In this case, the stack consists of 90 sheets, each just 200 microns thick. As mentioned previously, both of these motors are single-phase brushless DC, but what does that actually mean? Well, the vast majority of electric motors are three-phase, meaning they're connected to the supply with 3 wires, allowing 3 mostly independent currents to flow. Each of these currents produce a magnetic field in the stator that can be used to push or pull the rotor a little bit further around its never-ending circular journey. As I've only got 3 hands, let's just consider the pushing part for now. It's clear to see how a 3-phase motor like this produces a rotational force or torque, as there's always a linear force being applied at a distance from the axis of rotation, and torque is force times distance. Single-phase motors, however, are a bit messy, because there's only one controllable magnetic field rather than 3, which introduces a few big problems. The first is that they're quite hard to get going, especially so for permanent magnet motors like these. This is because, as we saw earlier when looking at cogging torque, the rotor has certain positions in which it likes to chill, and unfortunately for us, these are exactly where we're not able to produce any torque, because the force we can produce passes straight through the centre of the rotor, giving 0 distance and therefore 0 torque. The other problem with single-phase motors is that, when they are spinning, we have no way to control their direction because with just one current, we can only apply a force forward and backward, not left and right. Somewhere that we can all see a single-phase motor not knowing which way to spin is in a microwave, where the turntable will turn in whatever direction it feels like. While the direction of rotation doesn't matter in this case, it really does for Dyson. Imagine a vacuum cleaner suddenly blasting out all its muck, or a hairdryer sucking up all your hair, just because the motor's decided to spin the other way. So how have they ensured that it always spins the right way? Let's take a closer look at the vacuum cleaner motor to see what we can learn. Analysing the magnetic behaviour of the stator and rotor using finite element analysis software gives us these pretty colours, and reminds me that I should hurry up with this video so that I can revise for my exams. So let's take a step back and just consider the general stator geometry, which is quite funky. There's a clear asymmetry in the stator teeth, where these little lumps have been added to encourage the rotor to spin in the right direction. These are so effective that when I made my own controller for this motor a few years ago, I still couldn't get it to spin in reverse, no matter what control tricks I tried. Interestingly, the stator of the hand dryer motor doesn't appear to have the same asymmetric design, beyond this small difference in the width of the tooth wedges, which I think could just be me going crazy. So maybe Dyson have come up with some other control-based strategy for their newer motors. There's still one big unanswered question though. Why? Why bother with all this complexity just to remove a single wire? Well, unsurprisingly, there's more to it than just the number of wires. While design may be more complicated than it would be for an equivalent 3-phase motor, what you end up having to make millions of is simpler and cheaper to construct, because there are fewer coils to be wound, the stator doesn't need a continuous yoke, and the electronics is also simpler, needing only 4 switches rather than 6. These Dyson applications of moving lots of air very quickly are also perfect for hiding the weaknesses of this type of motor. There's essentially no starting torque, which makes getting going much easier, and high-speed operation allows the inertia of the rotor to smooth out the cogging torque, so that's only really an issue at low speed, hence why you only hear it when the motor's about to stop. These applications also represent very stable and predictable mechanical loads, meaning there's no need for complex control, reducing sensing and processing requirements. And finally, let's take a look at the part that I find most interesting, the rotor. Just out of interest, do other people feel the same way? What part of this hand dryer do you find most interesting? I think I can do some kind of poll in a YouTube video. I don't know how it works, but I'll put one here and we can learn together. Right, so what makes this rotor special? Well, you can tell from its grey appearance and sort of striped pattern that this has a carbon fibre sleeve.
That has a carbon overwrap rotor.
Which is usually something that's just reserved for high-speed motors used in sort of aerospace and motorsport applications. This is because the carbon fibres need to be wrapped extremely tight around the rotor, making it quite an involved and costly process, not very well suited to mass production. When you reach this kind of speed with a motor, you've basically got 2 options. Either have a rotor with a very small diameter to keep the centrifugal stresses that are trying to rip it apart under control, or if you need more torque and which both require a larger rotor, your only real option is to wrap it in carbon fibre like this, because carbon fibre strands have an absolutely insane tensile strength. So when this is spinning over 1,000 times a second, and the magnets are experiencing around 40,000 G, trying to fling them off the rotor at 120 miles an hour, these strands of carbon fibre will be put under tension, which is their speciality. In case you are wondering what this little cutout is at the end of the shaft, that hole will have just been drilled to balance the rotor, because of course at 70,000 RPM, balancing is quite important. Now, I think it's fair to say that the motor is the heart of the hand dryer, and the rotor, well, that's the heart of the motor. But there's actually one more layer of dissection to go, because the rotor has a neodymium heart. 4 of them, in fact. Now, cutting carbon fibre is pretty nasty because of all the particles you get off it. It's a bit like asbestos. So to stop them from getting into the air and into my lungs, we're going to be cutting this underwater. Doesn't help that the knife sticks to the magnet. It was so straight at the start. Now you're supposed to use special blades to cut carbon fibre like tungsten carbide or diamond coated, but as this is quite thin, I think I can probably get away with a nice fresh steel blade. Oh. You can see here a little piece of the enamel coating that they put on to hold it all together. Ta-da! Not quite as exciting as I was hoping. I'll get these bits dried off and we'll take a closer look. Here it is. I'm not going to lie, it's a little bit underwhelming. I'm not quite sure what I was expecting really, because it seems pretty obvious now that a mass-produced product like this isn't just going to use 4 off-the-shelf magnets tied together with carbon. It looks like, similar to the vacuum cleaner motor, this is actually just one single magnet that's been very cleverly magnetised to behave like multiple magnets. It's quite cool. And this means the carbon sleeve isn't here to hold magnets to the rotor, it's actually here to keep the single magnet in one piece, because the neodymium iron-boron alloy used is very brittle, and has a tensile strength about 100 times lower than carbon fibre. There's a little serial number on here too. I guess that's all internal stuff, so we have no idea what it means. Maybe it's someone's phone number. I must admit though, one thing I'm quite pleased about is that it's still going to look just as impressive on my shelf of cool things. And the carbon sleeve came off perfectly. How cool is this? A tiny little tube of carbon fibre that I can just slide over the shaft to show off to anyone that ever sees my shelf. On that depressing note, it's time to end. In just 30 minutes, we've reduced a hand dryer all the way down to a single magnet. I hope you found it as fun and interesting as I did. Thank you very much for watching, and until next time, bye!